all the models which are invariant under rotation, translation, and dilatation. So if you give me a critical model in abstract term, I don't know it. I'm not doing that. I'm classifying already models which has already built in these symmetries. So for this reason, I never question. Clear? Was already built in. There is nothing to be questioned about. Okay, now what is the key point of the story? The key point of the story is that this null vector is a differential equation. Has to be compatible with the operator pro expansion. This is the key, guys. This is the key point of everything. The key point. Let me show you how the story is implemented. So this I need it. Probably I will erase this one. I will come back later. So what I want to say, I can pose these very innocent questions. But the answer will be very interesting. The answer will be, let me take as a primary field the one which has a null vector at the level 2. And let me ask, if this guy make an operator pro expansion with another primary, what the hell can be here? What kind of fields can appear on the right-hand side? Okay? This is my question. And the answer is, whatever will appear on the right-hand side should be compatible with the second-order differential equation that this guy satisfied. Now, you remember how you solve hydrogen atom? Hydrogen atom, what you do when you go to radial quantization, you make an educated guess. You say, my wave function at the origin goes like R to alpha. You plug in the differential equation and you get the value of alpha. Once you get that, the rest is expansion in series. Okay? So what I'm saying is you do the so-called singularity analysis. You have a function and you want to capture the singular behavior of that. So from this point of view, I'm just doing this one. So what is really here will be sum on delta prime, C12 delta delta prime, 1 over Z1 minus Z2, delta 1, 2 plus delta minus delta prime, phi delta prime. And I want to constrain what can be delta prime. Okay? Now, if you take this differential operator, you have to be a little more precise. L minus 1 is second derivative. This is simple. But L2, I told you, is not a simple differential operator. We worked it out this morning. Okay? So, if you apply this to this term here, and let me call X this combination. So X for me is delta 1, 2 plus delta minus delta prime. For X, you get this algebraic equation. Okay? See what I'm doing? I have a function here which is 1 over z to x. But this function, apply the differential operator, has to be 0. 0 at the leading order. So this means that this function may have higher order, but I'm imposing order by order to be 0. So if I take the singularity, this is the equation which fixed x. And here is the surprise. You see that since this guy satisfies a second order differential equation, there are two solutions. This means in this operator pro expansion can only be two channels. Remember the story. The story is you are fusing two fields and you want to know what is here. In particular, how many primary fields run there? Because we already say that the descendant is taken account by the non-zero coupling of the primary. So the only question I have to put is how many primary run in that channel, because infinite number is ensured by the family. And so I'm discovering that if I take the operator pro expansion of the field which has a null vector at level 2, fusing with any other conformal fields, on the right-hand side, there can only be two primary, because X here is a solution of a second-order algebraic equation. Okay?
So you're doing a Frobenius expansion sort of for this differential operator, you expand this pilot series, and then you try and Jacob is going to leading order.
No, it's
these three, I'm questioning, these coefficients could have been computed, like the coefficients of this second order.
This one.
Okay. Like, could we have guessed, what can I say about the roots of this equation, let's say, without even solving it? Just based on...
Not really, Harry. Look, go and check how you solve hydrogen atom. It's exactly the same story. A differential equation of second order, you pose, in that case you pose is R alpha to some function. When you substitute these answers into the differential equation, you get immediately a condition on alpha. Okay. It's exactly the same. And it's something that has to hold order by order in any power. But the leading order is what you get. Okay? So far it seems pretty okay, you get something like this. But now, let me draw your attention on something that you will jump on your chair. The thing is, what about if delta is the degenerate field itself? So I'm asking, what is the fusion rule of 1, 2 with some other field Nm, which belong to that table? And the answer is stunning simple. What you get out of here, forget about the coefficients, because the equation are linear. I can never fix the coefficient. I can tell you the singularity, but not the coefficient. Not yet. What can be here? Can be the channel n m plus 1 and the channel m minus 1. Amazing. What is amazing? What is amazing is the following. Take this Katz table. If I take any fields of this table, and I ask, what is the operator pro expansion with 1, 2? I get either this or that.
Where is the 1, 2?
The 1, 2 is here.
I just see n and that.
Eh?
I just see n and that. So the solution just depends on n and that. I don't see...
Yeah, I'm just saying, if you substitute there, okay, if you take delta to be delta R and S, this equation is an equation for delta prime. The delta prime are going to be delta R S plus and minus 1. Look, step by step. I'm just saying, if I want to make compatible the operator pro expansion with 1, 2, is an example. And I ask, what can be the operator pro expansion which involve the field 1, 2? The answer is, if this field is degenerate as well, the answer will be a degenerate field as well. Not only, but I can predict precisely which field of which. You do the same story with 2, 1. With an arbitrary degenerate field, the things will be n minus 1 m plus phi n plus 1 m. So this means that if you take any fields which are degenerate and you make the operator cross expansion, you move like this. I think you understand where I'm heading to. 1, 2 and 2, 1 are like what is the PlayStation, joysticks. I can move on the left horizontal, applying iteratively the field 1, 2. And I can move vertically, apply the field 2, 1. So for instance, let's do some example. 1, 2, 1, 2. If I apply this rule, it has to be 1, 1, which is the identity, plus the field 1, 3. Okay? Now you remember my easy model? My easy model was 0, 1, 16, 1 half. So if I take this one, imagine magically I call this guy sigma. What I'm telling you is that sigma sigma times these fields which I call epsilon. So in field theory, epsilon is the normal order of sigma square. Okay? This is the algebra of Ising. The energy in Ising is the square of the magnetization. Square in field theory language, normal order. Okay? So, I can apply this. So you see immediately that all the fields which are along this direction are essentially power law of phi 1, 2, normal order to the power n. Right? Because I can keep going. I can ask, for instance, what happened phi 1, 2, phi 1, 3? And this keep me going. And here is these brilliant things. These brilliant things. Now, this is crucial in all the story. Crucial in what sense? So, the operator delta Rs is associated to a differential operator of order delta R times S. The same operator, so physically it's the same fields, is however algebraically associated to another position and therefore to another algebraic, sorry, to another differential equation of different order. Now imagine that you have a function which satisfies a second order differential equation and a 26 differential equation, order 26. What you have is condition. Namely, since are linear, the number of independent solutions are equal to the order of the differential equation. So if you have a differential operator of order 56, you have 56 functions. But if this guy has to satisfy also a second order differential equation, not all the 56 functions are good, only 2 of them are good. Clear? This is crucial. So what I want to say is that from physical point of view, the same physical fields, algebraically, they sit in 2 different positions, and for what algebra is concerned, they satisfy 2 different differential equations, but really of different order. So from this point of view, the 2 has to be compatible. So let me show how this make the story absolutely stunning, and how at the end I can have an operator pro expansion which is fully consistent with a finite number of primary. So let me take once again the easy model as an example. And let me focus on this guy here. So this guy here meant as operator 1, 2. I ask, what is sigma sigma? So according to the rule, this will create family, which are the identity, which is 0, plus this epsilon. Now this notation I'm using is just a notation we capture the singularity of the operator pro expansion. So you see, I'm not putting any power, I'm not putting the structure constant, because the power are rigorously fixed by the dimension. So it's a redundant information. And the structure constant, this level I cannot fix because the equations were linear. The actual value of the coupling will come up later. So at this stage, I'm just saying, if I do the operator pro expansion here, what will be on the right-hand side? So these are the anyons. So which one appear on the left-hand side? Without caring about the value, the real value C. In this formulation, C is only 0 and 1. Okay? Now, what about if I take the field 116, one of them I interpret like this. So this guy is 2, 2. 2, 2, if you see immediately, is essentially phi 1, 2, phi 2, 1, normal order. So if I do the operator pro expansion in the way I did it, a field which is here will create fields which are outside, like this, in diagonal. Because 1, 2 move one step right, and 2, 1 move one step up, in all possible ways. So if I take this operator pro expansion from this point of view, what I'm going to write, this guy satisfies 4-order differential equation, so I should have 4 families on the other side. So I get 1, I get epsilon, which are good, I get this, and then I get some crazy fields here. Let me call X and Y. But the two things has to be compatible. Therefore, the structure constant of these two fields, sigma sigma to X and Y, are rigorously 0. Once they do not couple to the primary, they do not couple to any of their descendants. So these fields, if you want, are there, but are sleeping. They don't do anything. So the nice thing of the nice way of thinking the CAS table is taking this value for the entire plane. You run RNS for any values. So you will have a full plane full with numbers, which are these anomalous dimensions. But the point is, the only one which couple together are those which fulfill this restriction. Okay? I can prove it in general. I'm just giving you some example. Yeah.
How do we get this?
Yeah, I get because if I want to get here, is essentially I'm doing so.
And before just moving right and up.
Do this one. So if you make this from this point of view, is moving this field to the right or to the left. Here I'm anticipating this field will never couple, so will be 0. If you do vice versa, interpret this under the action of this one, you are taking this, you are moving up. And then you are moving down. But this guy is once again 0. Okay? So, in a nutshell, if we are able to solve the dynamics of the field 1, 2, and 2, 1, we have done. Okay?
It is true that by combining two primaries,
Yeah.
I obtain a primary field.
That's what I show you.
No, I mean in general. In this case, I can trust for the minimal models that this is true. But
No, it's general. Yeah.
okay.
No, because the structure from the algebraic point of view is very restricted. You cannot have a couple to a descendant fields without couple to the father. It's impossible.
So I cannot produce descendant fields
Without using the primary. So you will produce an infinite number of descendant fields, infinite. But there is always the coupling to the primary.
Okay, but
Is what I proved this morning. The structure constant is the coupling which tell you which one is coupled to whom. You cannot have a non-zero 3-point coupling to a descendant without being a non-zero at the level of primary. You cannot have. You simply cannot have.
So are these dormant fields, you explain, a consequence of this symmetry?
Absolutely.
Okay, could you please again explain the link, because I'm lost in this explanation.
So the point is, so the key point of the story is, so let me tell you in a nutshell what it's about. From the Katz table and Katz analysis, you end up to a set of rational numbers with certain restriction. Now, each of these numbers, the way you have to understand is that the fields, which has anomalous dimension delta Rs, satisfy a linear differential equation of order R times S. If they sit in two different points of the Katz table, they satisfy simultaneously a linear differential equation of different order. Now, the beautiful things of linear differential equation is that they span a linear space. So you know a priori the number of solutions. So a linear differential equation of order 81 will have 81 solutions. Now you have to fix it according to the boundary condition. So the general solution will be linear combination of this number. The fact that the same field satisfies two different differential equations put, of course, a condition on which of these solutions are the physical one. Okay? This is a general mathematical statement. Once I specify that linear differential equation associated to this field to the operator pro expansion they satisfy, I'm able to constrain severely what are the fields which I can produce on the right-hand side. Because it has to be compatible with the differential equation they satisfy. So if I give you two fields there, on the right-hand side cannot be an arbitrary fields. The singularity of that field has to be compatible with the differential equation. And I show you the example of the field 1, 2. So if you do the analysis 1, 2, you understand that the operator pro expansion, the field 1, 2, with any other degenerate field, will produce two degenerate fields, which are simultaneous left and right of that. 2, 1, up and down. Okay? Now, once you understood this, the rest you can keep going. So, for instance, if you do the field 1, 3, so you can ask, what is the field 1, 3 doing to NM? You take the null vector, you write down the differential equation, do the singularity, and what you get NM plus N minus 2, so probably it's the way around, NM minus 2, NM plus 2. So you are doing random walk, really random walk. So the operator 1, 2, and 2, 1 move you 1 steps. 1, 3, on the other hand, from this point of view, you see, was phi11 plus phi13. This guy is the identity. Remember that the way you define normal order in field theory is you subtract the identity, you take some limit. So 1, 3, from this point of view, is nothing else than apply 1, 2 twice. And so if you are a random walk, if you apply twice, you can go 2 steps further, 2 steps further, but you can come back also to the origin. And this is the operator for expansion. With any fields, either you remain to the same origin, or you move 2 steps away. Okay?
Why did we discard x and y from this construction
there? We discard because the operator for expansion and the singularity analysis associated to it has to be compatible, independent on the channel how I do it. So any fields admit 2 things. So once I compare the 2 things, I should find on the right-hand side all the common channel of both differential operators. Okay? So there is a complete analysis which we cannot do here, although you can understand what is the origin of that, because any fields NM, I told you, you can represent as some kind of normal order these things. And so there is the general fusion rules, which is the following. The fusion rule is this. The field phi n1 composed with field m1 and 2 this is the final algebraic result. So what I mean is, if you want to know what is on the right-hand side, here up to C, the actual value, C is only 0, 1, so it means whoever is there. Composition of these 2 degenerate fields, this is the field which can appear on the right-hand side. Remind some formula. SU2, composition law.
Do the quasi-primary fields go in the action or
No,
not?
no, they got?
Go in the action or not?
No.
So it's
Absolutely, they do not play any role. As I said, all who is running the business is the primary.
how can we see it? You see this in theory?
No, I proved it this morning. I say all other structure constants are obtained by the primary.
But they're still independent.
No, the primary has to be independent.
The others you say don't carry the information.
No, because they're descendant. So, for instance, in the level 2, L minus 1 square is not a quasi-primary, but L2 is a quasi-primary. But I can get the eigenvalues, the correlation function of this simply by the differential operators. So really, I don't care about the quasi-primary, at least at this level. I can care for different reasons at this level. Sorry?
In what sense are these theories unitary? You mentioned that they're unitary.
Yeah, are unitary in the sense that all compute are positive definite. I can never have anything negative. For instance, an example of negative non-unitary minimal models is what is called what is called Yang-Lee models. Correspond to P equal 2, Q equal 5. So they are coprime. If you compute the central charge according to that formula, it turns out to be minus 22 over 5. And the cut stable is 0, minus 1, 5, minus 1, 5, 0. And so you see that even though I can put this guy to be, let's say, normalized to 1, if I go and compute the norm of the descendant already at the first level, this you remember was 2 delta, delta, delta. This vector will have minus 2 over 5 as a norm. So the theory is not positive definite. You have to be very careful when you do complete set of states. Now, this is very interesting, but this will require not even a lecture, a journal club. Now, this is absolutely stunning model. This is, okay, you provocate me. So what is about this? You have to know that an alternative formulation of statistical mechanics is in terms of grand canonical partition function and zero thereof. If you study the zeros for the easy model, in the complex plane of Ophiuchasity, they are on a circle and they have some age singularity. No, but the story is more interesting than that. More interesting. The story is this ending point has a non-analytic behavior. So the density of this fixed point, or these zeros, the rho, are very anomalous here. So the question that Michael Fisher posed was, if I have a whatever that is anomalous, I know that I can describe in terms of field theory. So what is the field theory associated to the zero of Yang-Lee? And the answer is absolutely interesting. The answer is Landau-Ginzburg, but with imaginary phi-cube coupling. It's phi-cube theory. But phi-cube theory, if the coupling in front is real, does not make sense, does not have a ground state. But with I, maybe. And actually, you can prove that this theory is not Hermitian, but is CP invariant. And CP is the only equation, essentially, the only condition you need to have a physical spectrum. Okay? So, this Yang-Lee model, this conformal field theory, is providing for you the exact solution, this Landau-Ginzburg, at the critical point. But you have to pay a price. The price is that the dimensions are negative, because it's not Hermitian. So there are some imaginary things.
So this way, when you already tell these sections, they find complex.
You can, but I mean, at this point, you have to give up really unitarity. You have to give up completeness in the usual sense of the word. For instance, the completeness of this theory is not the usual one, n equal 1. It's not. The completeness relation is minus 1 to the n equal 1. So all the odd channel, you are weighting negative. And the reason that is very deep, because when an operator, the bra, so the left vector is equal to the right vector. The matrix is not symmetric, the bra vector is not the left one. And so there are matrices between them. In this case, there is minus 1 to the n. So I want to say you can do a lot of stuff, but you have to generalize things. So you have not to take it for granted the usual formula. Okay? Andreucci.
Sorry?
No, I think he's referring to you.
Yeah, no, but what we were discussing,
Ah,
can you have a conformal limb-like equation? Something like this.
this I don't know. Honestly, I don't know. Maybe, yeah. No, referring to you because he was referring to you before. I don't know. No. Forget. Sleep. Don't worry.
We got the gram matrices and order n, and we were looking for the solution of those.
We are looking for the zeros.
What is it that they have to check? And then Katz found out that the solution of, like, there is some constraint on those kind of solutions.
Yeah, that's I told you. So, if you face directly to solve this algebraic equation, you end up in terribly branching, terribly arbitrarily large radical of order n. Then you understand already from the first that there should be ranges in C. So I'm building up a lot of knowledge. It's not simple to provide at once all this infinitely larger knowledge. I'm just telling you that from the simple example, you understand there are range of C where something might be defined usually, something might be crazy, and so on and so forth. So from the first explicit solution, you understand that C less than 1 might be a good point. Knowing that, Katz parameterize the value of C for less than 1 in this specific way. And then they say, if you do that, the root of the determinant turns out to be rational.
So those are the old and only solution rational.
For C less than 1, yeah.
And so that's a smart way to parameterize all the rational solutions.
Yeah.
Imagine I have a lattice model and tuned to a critical point. When do I know that the total theory applies to this critical point?
It is a very good point, yeah. As I said other times, if, for instance, your lattice is honest lattice, so in the sense is at least 90 degrees of rotation, as local, so no long range, and stuff like this, pretty sure it applies.
Then to be so this kind of conformal theory we're using also applies to one-dimensional quantum.
Yeah, okay, then this is, you have to do the proper Hamiltonian limit and stuff like this, yeah. For instance, if you have a model like chiral Potts model, so something which is tendentially in one direction, you have to be a little concerned what's going on. Or if you have a long range, you have to be a little concerned what's going on. But the beauty of these things is so general that essentially apply always. So indeed, from the exact solution of this theory, you find many more than what were known before. And by the way, I'm restricting myself just to Z2 group. So what you can do is changing the group and repeating the same exercise. You will have extra generators, of course, to play with. The primary will be defined with respect to all, asking what are the representation which are reducible. You find out the same kind of Katz determinant, and therefore you classify things. So you can have, just random example, you can put supersymmetry in it. So you have, instead of T, 2 extra fermionic generators. Is the one I was giving you operator for expansion this morning. Probably not. No, I give another example this morning. So if you take operators which has this kind of operator pro expansion, C over I think 3. You can rephrase this operator for expansion in some anti-commutator for the Gn, the mode of this, and then you see, roughly speaking, apart this channel of identity, this is an energy. If you know a little bit supersymmetry is a symmetry in which the square is an energy. So this generator will enlarge your algebra to have a supersymmetry. At this point, you might ask irreducible representation with respect to the Ln and this Gn. You will define minimal model or supersymmetric type. There are many beautiful models. The Gaussian model is one of them. Kosterlitz-Thouless is another one, and many others. You can change the other group of symmetry in taking E8. You can classify the minimal models E8. You can take the symmetry Zn, which is called parafermionic. You go it, repeated exercise, of course the algebra increase substantially. You end up infinite number of fixed points with that symmetry, among which Ising, because Zn, if you put n equal 2, is Ising, you find it. Z3, Potts model, you find it, and so on and so forth. So these are the rule of the game. Once you define the group of symmetry, you have corresponding generators for the current. They enter at the same footing as the stress energy tensor, and you are asking irreducible representation of an extended algebra. Primary field of that algebra will be that field annihilated by Ln positive, Gn positive, and whatever else. And then you build up representation in it. You ask, are they reducible? So Katz determinant. Differential equation, the same kind of things. Fusion rules are severely restricted. Okay? So these are really the leitmotif of the story. And the beautiful thing is that these minimal models, this one, which are built up on a finite number of primary, are able to make self-consistent operator for expansion. This is really the key point, that I can build up using a finite number of primary, an operator for expansion which is self-consistently closed in itself. So at this point, the only thing which are left out is how to compute the structure constant, because so far I'm just saying, is there or not there? And tomorrow I'm going to tell you a very dirty trick how to compute it. Okay? And this will come up a bunch of gamma functions. Highly non-trivial stuff. Okay? So this is essentially the theory of minimal models. As I said, there are many variations on it. You might be interested in solving Liouville. Liouville is a very difficult conformal field theory, where such structure of the general field do not apply. How to do it? Is require other kind of techniques. Yeah.
Could you generate this kind of geometric differential equation you mentioned from the differential operator, so on the lecture?
Yeah. I will write down the differential equation explicitly. Yeah.
This will be next.
Yeah, next time.
So you said before that if we know 1, 2, and 2, 1.
Morally, we know everything. Morally.
But 1, 2, and 2, 1 depends also on the choices P and Q that we make.
Yeah.
We take P and Q.
So P and Q, the rule of the game is you take a pair of quasi-primary number, this fix C. C is the fingerprint of the class of universality. It's like when you cross the border, someone asks, who are you? You say C. My C is 710. I know what you are talking about. If you say my C is 6/7, it's Potts model. If you take whatever, this number uniquely characterizes the class of universality.
So we fix P and Q, we fix C, and then we study the P1.
We have to study the operator for expansion, compute this number, C. So we are now at the stage in which we have identified a fixed point according to the value of C, at least in some range. I know even the spectrum of operator, and the only thing which is left out, once I know the fusion rule, is to pin down the actual value of the structure constant.
And once C is fixed, we can exit we are always working with the existing. We cannot like go to two different representations together, like C1, C2.
No, this is the, I know what you mean, but this means a tensor product, but not simultaneous, not. What can happen is a flow between two theories. But this is different what you are thinking. When it's a flow between two theories is absolutely interesting, because what happens is that the correlation function, of the same correlation function, if you probe in one limit, it appears the spectrum of one theory. If you probe in the other limit, appears the spectrum of the other theory. This is the most you can do, but you cannot match together things. It's like you say, I have a representation, a 3/2, a 5/2 in spin. Can I do together? No, each one is its own. You can combine together, you can do something, but not simultaneously exist the things.
But here we are combining.
No, we are not combining. So this is what I say. So it's, any theory is strictly defined by these numbers.
After all this reasoning, is it always possible to build an action for a theory or not? Because
Yes or not. So formally,
this, we never talked about an action.
yeah. So your colleague is asking, given all that, if I have the model P equal 32, can I have a Lagrangian for it? Can I have a representation in terms of it? The answer to this is, first of all, I don't care, because I have all the rules to compute whatever I want. So this is an extra. So Lagrangian, in the most cases, the best you can do to compute something, according to perturbation theory. But if I really want a Lagrangian, I can. And the reason of doing is this. Okay, I will do this and then I have to rush myself. So when you have the CAS table, and you ask yourself, what is among this field the one which has minimal anomalous dimension but not zero? The answer is this guy here. So let me promote this to be the most relevant order parameters of my theory. So whatever sit here, I call phi. At this point, I do phi operator progress function. What I get, I will get this one, this one, this one, and this one. With powers. So I will get 1 over z 2 delta plus 1 over z blah blah, what is here, plus blah blah blah. Now, among these 4 channels, which is the one which has highest, so lower dimension, is this guy. So this means that if I subtract the identity, multiply by the power which is here, and take the limit, I select these things. So this will be the phi square. You keep going iteratively. If I do operator progress function this with this, what I get, once again, you get, the most one is here, phi 3. You get here. You climb all the CAS table. Once you arrive there, you are stuck. Because once you try to repeat the story, you end up to these equations that whatever you get here, you have to identify with this kind of stuff. What is this? This is the equation of motion of a Landau-Ginzburg things. So you can associate this to a Lagrangian, which is phi 2p minus 1. 2p, yeah, it's like this. Okay? So, say differently, any of these minimal models I can associate to a Landau-Ginzburg if I really want, because the equation of motion is exactly those of a Landau-Ginzburg for any purposes. Also the parity turns out completely right and this and that. If you take the, yeah, no, but these are massive. These are massive. These are massive clearly. These are massive. Yeah.
Because I was thinking to Lagrangians, which don't have, which are where the potential is an analytic function. So
Yeah, no, but this, what it is essentially potential, which become more and more flat to the origin. But to be honest, you have to reverse the story. Namely, conformal field theory, with all the correlation function that you can compute exactly, as a matter of fact, provide the exact solution of Landau-Ginzburg, not vice versa. Because solving Landau-Ginzburg is notoriously difficult. You have to do perturbatively. Resumming diagram, renormalize it, I mean, it's hell. So, essentially, you reverse the logic. Since you know that these minimal models are associated to Landau-Ginzburg, the correlation function you compute from it, we do tomorrow, provide, as a matter of fact, the solution of the Landau-Ginzburg at the critical point. Okay, guys, see you tomorrow.